Our goal for today is to establish that there's a difference between CFL and all. So what I'm saying here is that we have the set of all the different problems, all the different subsets of languages, which is just the power set of sigma star. And then at the very bottom, we have Finn, which has languages like 0, 1. Then we have the regular languages, which have languages like 0 star, 1 star. Then we have the context-free languages that have languages like 0 to the n, 1 to the n. Now right now this boundary right here is not something that we've proved, it's just something that I've asserted that is the case. So that's what we're going to prove today, that there's actually a difference between those. We want to prove that all does not equal CFL. Now the way that we can do that is by proving that there exists something x that is inside of all where x is not inside of CFL. Now, how did we do that before? The way that we did that before is we first proved that there was something that was true of all the different regular languages. If we convert that idea to CFL, what we're going to do is we're going to choose some property P, Then what we're going to do is we're going to prove that for all languages A that are inside of CFL, P of A is true. That means that there's some property that is in common with all languages that are context-free. Then what we're going to do is we're going to show that there exists something that is inside of all that does not have the P property. Then what we're going to do is then we're going to conclude that X must not be inside of CFL because everything inside of CFL has this property. As an analogy, we might say something like all humans, so we'll say that like A are humans, and we'll say that, all humans have, I don't know what all humans have. There's everything I'm thinking of, I can think of people who don't have that, you know what I mean? Maybe I guess all humans have at least one heart. Are there people who are born without, with multiple hearts? Maybe we'll do that. But then the thing is that there are things that are not. Okay, yeah. So we'll say that all humans have a heart. Okay, so now we know that all humans have hearts. Then what we'll do is we'll show that there's an animal that doesn't have a heart, or there's, all is animal, so there's something that doesn't have a heart. Therefore, that animal is not a human, therefore not all animals are human. That's kind of the idea of what we're doing. Okay, so this is the structure of what we're going to do today. We're going to say what the property is, then we're going to, we're actually not going to do step 2 today, we're just going to do step 0 and 1 today. Now recall, what was the property for the regular languages? We had the regular pumping property, and it looked like this. It said, so RPP of A was equal to, there exists some P inside of N, and we know that P is equal to the number of states inside of the machine, where for all S that is inside of A, such that the length of S is greater than P, greater than or equal to P, then there exists strings X, Y, and Z inside of sigma star, such that S equals X, Y, Z, and the length of X and Y is less than P, and the length of Y is greater than 0, then for all I inside of N, X, Y to the I, Z is also inside of A. And the reason that we knew this was true was because we know that every regular language has some DFA associated with it. And that DFA has to have some starting state, and it has to have some set of transitions until it gets to some state, R, and then there's some more transitions, and then it must eventually come back to R. And we know that it has to come back to R in less than P steps, if this is x and this is y, because we know that every step could, at sort of best, if it was trying to always go to new states, it could only do that p times before we'd have to see the same state a second time. Then there could be more state transitions until it ultimately got to an accepting state. And once we know that the DFA has to have a structure that's like this, we now have a recipe for deriving an infinite number of other strings that are in the language, because we can either exclude y, which is when I equals 0, or include it 10 times, that's when I equals 10, and so on. So what we need to do today is we need to establish a similar property that is true of all regular languages, of all context-free languages. So let's think about that. What is limited in a context-free grammar? Limited, i.e., in the way that states are in a DFA. Well, let's remind ourselves what a context-free grammar is. So if G is a context-free grammar, then that means that it has V, sigma, R, and S. S is just some variable. R are the rules. Sigma is some set of terminal characters, but V is a finite set. Okay, so context-free grammars, the thing that limits them is V. All right, let's assume G is in Chomsky normal form. Remember what Chomsky normal form means. It means that there are only 3 kinds of rules. There's S goes to epsilon, which might be there or might not. There's a variable goes to 2 variables, or there's a variable goes to a terminal. Those are the only kinds of rules. So this is useful for saying something simple about the grammar. All right. So now that means that V is some set of variables. We'll call them V0 through Vn. Those are all the variables. And let's just assume that S equals V0. Now, what we are interested in is when is it the case that we can force the context-free grammar to run out of variables and be forced to use one a second time. What does a derivation like that look like? So we know that the start symbol is V0. Well, if the goal of what we're imagining is let's imagine a long string, and we want to make that string as long as possible before having a second instance of the same variable. Now, if we want this to be long, we don't want V0 to go to epsilon because that's small. We also don't want it to go to a terminal because that's small. Therefore, it's going to go to 2 variables. Now, it could go to 2 different variables, but if it went to 2 different variables, then that means that it would spend 2 variables in one step. But if we wanted to make it as long as possible and delay seeing a variable a second time for as long as possible, then what should happen is it should use the same variable twice. Okay, so we have V0 goes to V1, V1. Well, then each one of those is going to have a rule as well, and what it would do is it would go to V2, V2, that's what the first one would do, and then V2, V2, that's what the second one would do. And obviously we would continue doing this. We would continue doing this until eventually we got to Vn, and how many of them would there be to Vn? How many of these would there be? Well, a way to think about this is that we start with a tree that has 1 element in it. Then we take that tree and we expand it to have 2 things. Then we take that and we expand each one of those to have 2 things. Okay? So what we're interested in is we want to know how many things are at the bottom when the height is n. So an n height binary tree. How many nodes are there at the bottom? The number of nodes there are, I believe, is 2 to the n minus 2 to the n minus 1. Is that right? So this right here is height 1, so it has 2 to the 1 minus 1, so that's 1. And then this one would be 2 to the 2 minus 1. So 2 to the 2 is 4 minus 1. Okay, so that's the number of total nodes that there are, but we want to know how many leaves are at the bottom, and how many leaves are at the bottom is just 2 to the n. So the number of leaves would just be 2 to the n. In this case, n is the size of the number of variables. Okay, so that's how many leaves there are. And at that point, if every single one of those then transitioned to a terminal, that means that the total length of the string would be 2 to the v. Okay, so what does this mean? This means that every context-free grammar, if it's going to be long, what's going to happen is that there's going to be the start symbol, and then it's going to have a whole bunch of derivations. And eventually it's going to get to some string that we'll call x. Sorry, we'll call it u. It's going to get to some string that we'll call u. And then there's going to be some variable r. And then after r, there's going to be some string z. Now r, what it's going to do is it's going to run for a while, and it's going to turn into some string v, and then another instance of itself, r, and then some string y. And then r will transition eventually and get to some string x. And we know that this must happen if this part right here is at least n plus 1 high. And we know that because if this is n plus 1 high, then it's impossible for every level of the tree to get larger and never visit a variable multiple times if it's n plus 1, because if it's n, then that means that everyone will get to be visited. Okay, so what that means is that the amount of repetition that will happen is this part right here. So if this part right here is enough to force this thing to be n high, then that means that this has to be longer than 2 to the n plus 1 minus 1. Because that is how many edges there are going to be. Sorry, that's how many vertices there's going to be at the bottom of the tree that is that high. Because it's 2 to the n plus 1, and it's going to be bigger than that. Okay, so this idea right here is the core of the property that is true for all context-free grammars. And we can turn this into something that's like the regular pumping property, although it is called the context-free pumping property. The context-free pumping property, or CFPP. So it is about a language A, and here's the way that we write it. We say that there exists a P inside of N, and we know that P is equal to 2 to the length of V plus 1, okay, where for all strings that are inside of A, where the length of the string is greater than or equal to P, then there exists strings U, V, X, Y, and Z, where S equals U, V, X, Y, and Z, and the length of Vy is greater than 0. What's Vy? Vy is the part that gets repeated, the part that goes from R back to R. And the length of Vxy is less than or equal to P. Then for all I inside of N, now what is the string that's going to be inside of it? Well, notice that we can apply this rule that goes from R to R over and over again, duplicating V and duplicating Y. So that means that the string that must be inside of it is U, V to the I, X, Y to the I, Z. That must be inside of A. So let's look at a little concrete example of this. Okay, suppose that we're talking about the language S goes to epsilon 0 S1. Well, in this case, if we write down a string that's longer than the number of variables that are in this, and of course the Chomsky normal form of it. So remember, the Chomsky normal form had S prime, S, X, A, and B. So that's 5 things. So if we write something that's at least 5 letters long, so let's look at the string 0, 0, 0, 1, 1, 1. Oh, sorry, it's not 5. It's 2 to the 5. That's really big. But actually, it turns out that we don't need anything that big. So let's just do this one. So what we want to do is we want to figure out a way to divide this up into components to make this true. Well, U could be 0, 0. V could be 0. X could be epsilon. Y could be 1. And Z could be 1, 1. So clearly, this string right here is equal to this division of the characters. And we also know that U, Vi, X, Yi, Z is inside of 0 to the n, 1 to the n, because what is that? Well, what that is 0 to the 2 plus I, 1, 2 plus I. And so clearly that is definitely inside of this language because the number of zeros and ones are equal. Okay? So we have now established that there is a property that is in common with all context-free languages. They have this thing, the context-free pumping property, that essentially predicts the way in which context-free languages have to have repetitions. They have to have repetitions in a way that corresponds to the tree-like structure of the parsing of a context-free language. All right, so what we'll do next time is we'll talk about a concrete example of something that is inside of all but not inside of CFL.